Остановит. Да. I see. Okay. I see. Indeed. So I should make this announcement again. The new sheet for the exam is on the web page. There are 2 dates there, those for those who are graduating and those who aren't. And we were giving a new proof here of the Auslander-Buchsbaum formula. This proof I learned from a book of, I forget their names. So the book is called Cohen-Macaulay rings, and it's in the first 20 pages. I think Bruns and Herzog. Okay, so anyway, all we just did now was the depth of the ring equals 0 case, which we did last time anyway. So now let's give the positive depth case. So consider now, suppose that depth of A is positive, but depth of M is 0. Then consider a presentation. Consider a presentation of M. So M is finitely generated. It's projected onto by some number of generators, and there's a kernel. And I claim that now the depth of K is positive, in fact, equals 1. So the depth of K is 1, and whatever its projective dimension is, it's one less. So this is depth of M plus 1. Right, and why is this? So this follows from the Ext characterization. For the depth. So you'll remember that last time we showed that the depth was the minimal non-zero Ext from K into the module. And so if you look at the longest X sequence here, you'll find, well, here, if this is 0, there'll be an X0 from K into here. There will be no X0 into here because the depth is positive, and so that will force the X1 into here to be non-zero, and that will be the first non-zero X there. Okay, also, just because this is the beginning of a projective resolution for M, the projective dimension of K is 1 less than that of M. So if the Auslander-Buchsbaum formula is true for K, it will be true for M because this +1 and -1 will cancel out. So Auslander-Buchsbaum for K implies Auslander-Buchsbaum for M. And this means we can assume that the depth of M is also positive, because we could reduce to the case of K, which has positive depth. Okay, now I need to move cameras again. So we may assume depth of M is positive. But if the depth of A and of M are positive, it means there's a common non-zero divisor for both. Okay. So the maximal ideal is not an associated prime of A or of M. And remember, the associated primes were a kind of union of non-zero divisors. It's enough to prove it for things of positive depth. Because if I can prove it for K of depth 1, then I will get it for M of depth 0. And so there exists an F in the maximal ideal, which is a non-zero divisor on A and M. But then we can kind of just put together our formulas for depth and projective dimension that we know when we take modulo F. I think this was supposed to be on M. That's probably fine. I needed this for depth. Okay, so then the depth of A equals depth of A mod F plus 1. So if I quotient out by one of the non-zero divisors, I only have so many left. I also have depth of M, same kind of thing, depth. So this is over A. This is over. And also for projective dimension. So now we can put these together by induction. So the depth of A equals depth of AF plus 1. And then by induction, so induction on depth of A, this has depth 1 less than that of A, and so I can apply the Auslander-Buchsbaum formula to the module M mod F. So this will be depth of M mod F plus projective dimension of M mod F plus 1. So this is induction on depth A. And then what do we have here? This here gives depth of M. That's depth of M. And here, the projective dimension doesn't change. Because as we said, if I had a minimal resolution for M, then modulo F, it will still be a minimal resolution for M mod Fm. Okay, so that's the proof of the Auslander-Buchsbaum formula. And our main application of this formula, I mean, it's useful if you want to know something about the length of resolutions of M or something about the depth of M. But our main application is going to be to characterize regular local rings in terms of homological dimension. And for this, we need to recall some things about the Kazoo complex. So we introduced this in the seminar. We'll talk more about it in the seminar today. Let me remind you what it looks like. So given a bunch of elements in a commutative ring, the Kazoo complex, it's a complex that tries to resolve A modulo the ideal generated by these. And sometimes it succeeds, and sometimes it doesn't. So the Kazoo complex is, so what does it look like? In degree 0, it's just the ring A. So the Kazoo complex is called K. I'll write F underlined. In the next term, I have R copies of A. Then I have the second wedge power of R copies, and so on. And that can go up to the top wedge power, the rth wedge power. Beyond that, of course, the wedge power is 0. Okay? And I have to tell you what the differential is. Okay? So with differential, so if this is D1, then D1 of the ith basis vector is the ith element of the ring in this list. And the other higher differentials are defined so that the differential behaves like the de Rham differential. So it becomes a derivation, kind of dual to the de Rham differential. And so D of a tuple, so the basis for the wedge power consists of these wedge tuples where I1 is less than I2 is less than IK. So this will be Fi1 EI2 wedge EIK minus Fi2 EI1 EI3 EIK, and so on. So I leave out EI2 and then plus Fi3, and I'll leave out EI3, and so on. So it's a kind of alternating sum like this where I leave out different terms. Okay? So that's a Leibniz rule. For multiplication with respect to the wedge product, the differential behaves as a derivation, a graded derivation. And you may recall that we checked in the seminar, and we can check again. I think also in the other seminar, this was checked. So you can recall that it's possible to construct the Kazoo complex inductively. So recall the following. This Kazoo complex on a collection of elements, F1 through Fn, is isomorphic to a tensor product complex of doing it for F1, doing it for F2, and so on. So maybe just inductively, I would say, do the first n minus 1, and then add on an additional one. Okay. So we checked this, we can check it again. And what we're interested in is homology of one complex tensor another complex, tensor Kazoo complex. So, so notation. It's kind of nice notation. Given a module M, its Kazoo homology with respect to a sequence of elements is denoted so it's by definition. So the notation is the following. So the ith one, it will depend on f and on m. So you think of f as fixed and maybe m as varying. And this is defined to be ith homology of the Kazoo complex on this collection tensor the module M. So that's some new complex, and you can take its homology. That's the definition. And so when M equals A, we're just taking homology of the Kazoo complex itself. Okay, so we'll prove some more stuff about this in the seminar. Right now, I'm just going to prove enough to get our main theorem. So this Kazoo homology is something very useful and a big deal, and there are lots of things you can prove about it. But here's what we need to know right now. I'm going to double check my hypothesis. So a nice reference for this is a book of Serre called Local Algebra. It has the advantage that it's very concise and only tells you important things, not a bunch of things you don't want to know. Just a sec. Yeah, there's no hypothesis. Okay, very good. So the situation is the following. So let L dot, let this be some other complex. I think there are really no hypotheses. Yeah, I think there are really no hypotheses. So let this be a complex of A modules. And consider the tensor complex for a single element. So I should say that. So fix, this is going to be part of our inductive argument. So we fix an element of the ring. We have a Kazoo complex on that. It just looks like A mapping to A by multiplication by F. If R equals 1, right? This is just multiplication by F. And so consider the Kazoo complex for that single element, tensor this other complex L. And we want to know something about how the homology of this is related to homology to Kazoo homology on the individual parts. So then there are short exact sequences. Of the following form. So the ith homology of this tensor complex lives in a short exact sequence where I have the 0th Kazoo homology for this element F on the ith homology of the complex, and the first Kazoo homology of this element F on the I minus first homology of the complex. So this looks a little bit like a universal coefficient formula, if you like. So this is going to allow us to do inductive arguments. So I'll sketch the proof. We can go into more details in the seminar if you like. So you consider the following. So the ring A, considered as a complex in degree 0, embeds into here just as the 0th term of the Kazoo complex. And then the quotient is just A but shifted into degree 1. So you consider this. So you consider this short exact sequence of complexes. And now tensor with L since all the terms here are free, nothing breaks when we tensor. So we'll get a short exact sequence of complexes like this. So if I tensor A with L, I just get L. Then I'll get the thing I'm trying to understand, Kazoo complex of F tensor L. And then the quotient will be L shifted by 1. So that'll be a short exact sequence of complexes. Now I can take its homology. Okay, so now you need to check that in the long exact sequence of homology, the connecting map is given by multiplication by F. And that will follow because in this complex, the differential is just multiplication by F. And then the second thing you need to check is that for any long exact sequence, you could break it up into a bunch of short exact sequences by considering images and kernels and so on. So now break up the long exact sequence into short exact sequences by considering images and kernels of images. And you'll find these short exact sequences. Okay, so there's something to check. We can do that in the seminar. And the corollary of this, a corollary in a proposition, am I on the correct Yes, it's visible. So suppose the homology of our complex is concentrated in degree 0. Okay, so L, maybe it's not free, but it's like a resolution of M. Then, if F is a non-zero divisor on M, we get that the homology of the Kazoo complex of F, tensor this complex L, is just M mod Fm. So that will follow from the short exact sequence. The only kind of relevant term here, it's going to be I equals 0, and that's where I'll get the M mod Fm. And the second fact, kind of putting these two things together, proposition, if F1 through Fr is a regular sequence on M, then the Kazoo homology for this sequence on M vanishes in positive degrees. So in particular, this is the fact we really need. Suppose A is a regular local ring. If A is a regular local ring, then there is a regular sequence of maximal length. So I could take the minimal generators of the maximal ideal, and we saw that inductively, using the Kroll principal ideal theorem, well, it was a domain, so each thing is a non-zero divisor, and as I quotient by them, one by one, they form, inductively I get regular local rings of lower dimension. So then a minimal set of generators F1 through, say, Fr and M forms a regular sequence. On M equals A. So, so the Kazoo homology, so the homology of the Kazoo complex of this collection is concentrated in degree 0. So this is just the 0th homology, which is going to be A modulo the maximal ideal, because it's generated by the Fi's, and that's our K. So the Kazoo complex is, in fact, a free minimal resolution of K. And so we get this inductively using the tensor product formula. So tensor first with K F1, then with K F2, and keep applying this inductively. And And since it'll be a regular sequence on all the quotients inductively, you'll never pick up any higher Kazoo homology. Okay, let's go back to this board. So now we can almost proved actually half of the characterization of regular local rings. We've seen that if a ring is regular local, then its residue field has finite projective dimension. And we even see what it is. It's the length of the Kazoo complex, which is the number of minimal generators. So the theorem is the following. Let's see. Well, we have 20 minutes. 20 minutes. So this says, I don't know to whom this is due. Maybe Auslander? Maybe Serre? I don't know to whom this is due. So it says, an Ethereum local ring this is regular if and only if it's of finite homological dimension. And in this case, we have the following. So we always have that the depth is less than the curl dimension. Which is no more than the dimension of this Zariski cotangent complex. By definition of regular, this is an equality. So we'll actually achieve equalities for this and also for homological dimension of A and the projective dimension of the residue field. So all of these quantities are the same. So another way of saying it is A is regular if and if all these quantities are the same. So proof. So one direction is if A is regular, the preceding proposition shows that projective dimension of the residue field, while the residue field was resolved by the Kazoo complex on a minimal set of generators, the number of those is this dimension. And that, of course, is always finite. But we know that the projective dimension of any A mod I, well, of any module was less than or equal to this one. So we showed that last time. So somehow the most complicated module is the residue field. So A has finite homological dimension. And we also have the depth equality. So we know already that for regular local rings, the minimal set of generators, which is this number, is actually a regular sequence. So we're interested now in the converse. Conversely, And here I'll use a fact which we'll go back and prove in just a minute. So there'll be some lemma left over. So conversely, suppose A has finite homological dimension. In particular, the residue field has a finite minimal resolution. We're going to use the length of that resolution to bound something. So let's see. So we always have, for any local ring, depth of A is less than or equal to dim A by the Krull principal ideal theorem and used inductively. And this is less than or equal to this number. That number is called the embedding dimension. And so we need to show the reverse here. We need the reverse inequality. We want depth of A to be at least as big as this. And this is the number of minimal generators. Right. Just a minute. This is all good. Yes, very good. Okay. So now take a minimal set of generators of the maximal ideal. So let's say this is R. And we want to see that they actually form a regular sequence under the hypothesis that projective dimension of K is finite. And so this will give it, in fact, equality. So form the Kazoo complex. We want to see it gives a resolution of the residue field. And then this will make F1 through FR regular. So I should have stated this. We had this proposition in one direction. Where is it? It was over here. If I had a regular sequence on M, then this Kazoo homology vanished. In the local case, there's a converse to this, which we'll prove in the seminar. So this will use the converse to the last proposition. in the local case. So we can test regularity of a sequence by vanishing a Kazoo homology. And now what we're going to do is embed the Kazoo complex in the minimal resolution of K. And so we'll check this as a lemma. So claim the Kazoo complex of this collection embeds into, this is a split injection, this is a split injection into the minimal resolution of K. So how do I do this? Let's first construct the map. So the beginning of the Kazoo complex looks like this. And the minimal resolution also starts like that. But then there's some other terms. We don't yet know what they look like. So to begin with, there's an obvious identification here and here. And then using our usual lifting argument, where I have a projective resolution in the target and a projective complex up here, I can lift. Okay. So the map exists by lifting property for projective modules. We use this many times, for instance, when we were showing that X were well-defined independent of projective resolutions. And we'll check in a minute by a separate lemma. This is, we'll check in a minute. This is a split injection. And so, since it's a split injection, the homology of this complex is a sum of homology of this and of its complement. But the homology here is 0. Therefore, the homology here must be 0. So since the injection is split, the homology of the Kazoo complex is a summand of homology of the minimal resolution, which is 0. So the Kazoo complex is exact. And the sequence is regular. Okay. Therefore, the depth is large. So the depth actually equals the length of the Kazoo complex. Depth of A equals projective dimension of K, which is the length of this minimal resolution. And what else? This is also, well, all the other numbers. This was the number of generators. Okay, so it remains to prove this claim that this is actually a split injection. So it remains to see that the map from the Kazoo complex to this minimal resolution is a split injection. And we do this inductively. So it's obvious that the first few steps we're going to do it inductively. So we do inductively. So let's go out to, I don't know, level K, and suppose we've done everything before then. So consider wedge K. And there's a differential to wedge K minus 1. And I already know that this part of the map is a split injection into Fk minus 1. And I want to see phi k is also a split injection. So consider this map. And we're going to use this lemma we already had before, that if I want to check that this map is a split injection, I need to reduce it modulo the maximal ideal and see that it's an injection. And so we need to carefully analyze it to see why, when I reduce modulo m, it remains an injection. You have to be a little careful because actually if I tensor this with the max, if I take this modulo m, it becomes 0. And same here, because these are minimal complexes. So we need to give a little bit of an argument. So then note that this differential is given by, remember, multiplying with the fi's in front of some basis terms. That's what it looked like in formulas. And I know also that the differential of this lands in something in the maximal ideal times f, because it's a minimal resolution. So the note we have the following. So I have wedge k minus 1. I could reduce this. Yeah, how do I want to say this? I have in here, because this is free, I have the maximal ideal tensor k minus 1. This is just tensor this free module with inclusion of the maximal ideal in the ring A. And the image is stuff of the form maximal ideal, stuff in the maximal ideal times this, and sum over them. And because of the formula of the Kazoo differential, which is just multiplied by things that are in the maximal ideal, this actually factors through here. Okay, so this factors. And similarly here, I have the maximal ideal tensor of k minus 1. And the differential here also factors through there. Okay. So I can factor everything through here. So I'm going to consider that. So consider now this map. And I've already assumed that this was an injection by induction. Okay. So now I'm going to reduce all of this mod m. Tensor with a mod m. And we're trying to show that this remains that this becomes an injection modulo m. And this, so what do we get? We'll get the reduction of this, mapping to. So what happens to m if I tensor with a mod m? I get m mod m squared, right? So this remains an injection because I'm just tensoring over A with this module on these three things. Okay, so this remains an injection. This is what it is. And I claim that this is an injection, therefore the composite is an injection, therefore this must be an injection. So I claim this is an injection. And this will be obvious once we write down a formula for it. Okay. Let me call that d bar. So indeed, what does d bar do to a basis element? It looks like, before taking modulo anything, it looks like fi1 times ei2 wedge eik minus fi2 ei1 ei3 eik and so on. And its image in here, well, each of these lives in M. This is just the image modulo M squared. Okay, but the original FIs, they were a minimal set of generators for M. So they map to basis elements for M mod M squared, so they're non-zero there. So since the FI, a minimal set of generators, their images in M mod M square are non-zero. Okay, so now all of these elements are distinct as elements are here. It's a sum of basis elements and distinct basis elements. Okay, so this is non-zero. Right. I need to say a little more than that. I wanted this to be an injection, right? So I need to say that no two basis elements map to the same thing. So if I try to write down a matrix for this in basis elements, I want to say, like in any column, it's all zeros and a 1, and no two columns are the same. Right, so maybe I need to argue a little more for that. Let's see. This should be obvious. On the, just looking at the right-hand side, because all the coefficients of here are non-zero, if I just look at which basis elements appear here, I can recover this. So it was injective on the basis elements. Okay, so this is an injection. Therefore, since this was an injection modulo the maximal ideal, it's a split injection before taking modulo the maximal ideal by the original lemma. Therefore, the Kazoo complex is a summand in this minimal free resolution. Therefore, itself is a minimal free resolution. Okay, so we're done. And I think the one thing we really didn't prove is the converse to this proposition, that in the local case, vanishing a Kazoo homology gives that it's a regular sequence. So we'll need to do this in the seminar. Okay, let's stop there.